My name is Hao Wu, and I'm doing research with David Levinson at the University of Sydney. Today I'm presenting ensemble forecasting. So the modeling as a profession has come a long way, from the Greek oracles reading tea leaves to the statistical and controlled experiments which we use today. But the statistical method and modeling we use are not very old concepts. Firstly, models can be useful. Models show us what is likely to happen given all the available data and information. And models are generally more accurate than expert opinions. Models are also fundamentally flawed because models are computational procedures that add or multiply numbers, but many real-world events are not computational by nature. So the best models, which modelers often try to find, may not even exist. And models fail in different ways. The model assumptions can be wrong. The events may not follow the assumption exactly. And inaccurate measurements for explanatory variables may cause the errors to accumulate over time, including in the four-stage transport planning models. And the single model output from the single model predictions often gives a false sense of determinism and instability. So what the model does not tell you is the result really can be something else. And this figure shows the prediction, which is plotted in black line, for the vehicle miles traveled in the US based on single linear growth assumption versus the actual observed value plotted in red line. So when the assumption fails, the entire model prediction fails as well. And how to make the models useful is by using ensemble forecasting. In transport modeling, the ensemble forecast can be very complicated, but today I'm only talking about the combining models and combining data. Combined data, so if you have different data sources for a single explanatory variable, you don't have to make a random choice as to which one is real, is the ground truth. You can calibrate the same model multiple times, each time with a different data source, and combine or plot all the possibilities. Combining models, so you can either, for a single data set, you can calibrate different models with a single data set, and you can use either simple rules to weights or just use the simple average of the different model outputs. Or you can do it in a more complicated way by training method learners to combine the base model predictions. And you can also mix it up by combining both models and data sources, and even ways to combine models. We term this deep modeling. So if we compare ensemble forecast with single model doctrine, the ensemble forecasting is like a wise banker that combines different models and data sources. It is like combining different stocks. So if a single stock fails, it does not crash the entire portfolio, while the single model doctrine is more like a gambler that bets on which model is likely to be true, and good luck with that. And we show some examples of ensemble forecasts from outside of the transports. So if you do a Google search and you see all the probability of precipitation, and these numbers really came from thousands of runs by different models and with different perturbations of the measurement data. So the weather people run the model thousands of times, and they count the number of times when it rains and gives you the probability you see here, which is pretty accurate over the long run. And the weather people also use different models and data sources to predict the trajectory of hurricanes, which is plotted in the white line. And the mode of the ensemble models came pretty close to the actual track of the hurricane. The ensemble models also used in political forecasts. They have different polling data and different models, and they plot all the possibilities. And in this case, the ensemble model favors Biden to win the presidency. And we show an example here, which we use the ensemble model to predict the sales price of houses in Sydney. Please note the models at this time are not fine-tuned for accuracy. We only want to show how combining models can improve the ensemble forecast accuracy beyond any single base model. And for the dependent variable is the transaction price of houses in Sydney from 2017 to 2018. And the explanatory variable includes the house characteristics, the number of rooms, parking spaces, and building heights, and how large the land parcel is. And we include location characteristics, including social demographics and accessibility variables to explain the convenience by transport at each location. And this figure shows what the accessibility like in Sydney. So the same house will be more expensive in more downtown locations than in the city outskirts. For the base models, we have linear and a bunch of machine learning models, including classification trees, random forest, gradient boosting machines, and neural network. And we also have 3 different models to combine those base models, which we use as linear models, random forest, and gradient boosting machine. And if you look at the output from the ensemble models, this is an example of predicting the price of a single house, which is shown as the red line. And we have 7 data sets and 3 different models, which combined gives us 21 different model predictions. And we plot that on the figure, which shows a range of possibilities, which we plot as box whisker curves. So what the ensemble model does here is it shows the different possibilities. So you don't have to pick model or the data source yourself. So you don't end up like the 2 outliers in the figure. And ensemble models are also more accurate. This figure shows the ensemble models to have lower mean absolute errors than any single base model. And same story here for the mean square error. And some models also have more stable predictions. So the colored dots, the green and blue dots, are linear and gradient boosting machine meta learners, which produces the lowest standard deviation of absolute errors in its predictions. So a few takeaways. Ensemble models can be very useful. They improve forecast accuracy, and they provide a range of possible outcomes instead of a single model and a single outcome. And the bottom line here is that ensemble models are generally no worse than a single base model. So there's really nothing to lose by trying ensemble models in your forecast. Thank you.